Yeah, I think so. We're recording in progress. I think so.
Okay, good. Good. Yes, we are recording. Okay.
So now press until you,
yes.
again, it's until you go to slide number 8, I think.
Sorry.
So press again.
One moment, please, Professor.
Okay.
I don't know how. Here. Okay. And this. Okay. Okay. Yes.
Again. Next. So I will tell you when to stop.
Okay.
Again. It's until we get to the Wheeler-DeWitt equation. Don't worry. So that's my point. This is next. That's it. Before that. Before, just one step. Before, just go slow. Before. That's it. That's precisely. That's the Wheeler-DeWitt equation. I want to see the next equation. Bring me the next item. Precisely. That's it. Thank you. So that's the Wheeler-DeWitt equation, and you have this very funny looking derivative term. So we have a delta instead of the d. So delta is a mathematical convention where we use this for functional derivatives. This means that you have like an integral of many derivatives. So we are still doing things in superspace, which is the space of all spatial metrics that have dependence on all spatial coordinates. So this is very abstract. This is something that you can read on some references that I will point to you and in some books. But the point that I want to make now here is trying now to do something that can be workable. So now, please, Giovanni, please proceed to this slide number 13, which was the last slide from yesterday's talk. So please, again. So this is the go before that. Sorry. It means, yeah, precisely. Brilliant. So we need to do calculations. We need to do things that allow us to understand what is happening. So models that are feasible and realistic are what we call mini superspace. So this means that from all the metrics that you can consider for your space-time, for your universe, you are taking only one particular class, the homogeneous metrics, the ones that depend only on cosmic time. So the consequence of this, which is a very important mathematical and practical consequence, is that you now have a finite number of degrees of freedom. When you only have geometry and, for example, a fluid, you can bring time. We talked about this yesterday. And you can have a scalar field and you have a two-dimensional mini superspace. Or if you have a Bianchi model with more scale factors, for example, where you have an isotropy and scalar fields or vector fields. So this means more, but not too much. So you can do things here. It will become very complicated when you do some calculations, but it's still finite. So mini superspace, I would like just to mention this because I said this yesterday, is a challenge. It is a challenge because it is an open challenge. There is a question there which I wrote, what is the validity of this approximation? Can you really do mini superspace? Is mini superspace worthy? Yes, it is. It brings you interesting results, and you can obtain from it semi-classical corrections at different levels on quantum field theory in curved spaces. So this is something that you can apply in black hole radiation, for example, which is yet to be verified, and also in cosmology. But I will come to this in a moment. So mini superspace is what everybody does up to some point in quantum cosmology. I would like just to remind that in the last equation, the last line with the mathematical expression that we have there is something with a capital D with boldface and capital R with a boldface. These are the dimensions, or if your mini superspace. If your mini superspace is a scale factor, meaning Friedman, and one scalar field, then D, capital D, is equals to 2, and this term here goes to 0. If you have now an isotropy and a scalar field, you cannot bring this equals to 0, and you may need this. So this is something also that you are assuming an hypothesis. You are taking that you want conformal invariance. Then you tell me, oh, well, I don't want conformal invariance. I need some factor ordering that I choose myself. Fine, you do that. This is, in the end of the day, you always need to compute the solution and see if those solutions have any matching with the physical reality that you have. So I just wanted to say this, and then a new slide. So if now press now, how can we do things in mini superspace? So we need still to do approximation. So this is what we call as the WKB approximation. So we are trying to solve things in a way that our wave function has a particular hypothetical form. You have an amplitude, A, capital A, and then you have like the exponential of the classical or the Euclidean action that you write it as a WKB approximation. So you do this, so you can write as it is there with the Euclidean action when you are inside, so to speak, the barrier. So you are about to tunnel through, or if you are already tunneling, you will have there not the Euclidean, but you will have there the classical action, the usual thing that you use in classical mechanics. So if you can press again, Giovanni, please.
Yes.
Thank you. So the WKB is actually something that you have either for different regions. So the expression that is above is something when you calculate things either in the Euclidean action, but you can and you should do things broadly. Why is this so useful? So then if you can press again. Thank you. That's fine. Let it be there. So when you have now your Wheeler-DeWitt equation for a Friedman model with a single scalar field, your Wheeler-DeWitt equation, very simple, has that form. Again, please see that the Wheeler-DeWitt equation is for a two-dimensional mini superspace. You don't have that middle term that we talked about in the previous slide. And this is a very simple sort of Klein-Gordon-like equation. Moreover, if your potential for your scalar field is a constant or the cosmological constant, this becomes a easier case to solve. And if you don't have any potential for the scalar field, it is even nicer. You have Bessel equations for your alpha, which is just a representation of your scalar field, is actually the log of A, the scale factor, and the solutions for the scalar field are just plane waves. So this is very, very, very simple, but you can do things more complicated. You can assume that your scalar field has a non-zero potential, and then you have these two types of solutions, WKB. You have some things that are oscillating. The first line of solutions that I am in the last equation, or you have purely exponential, either dumping, say, decreasing or increasing solution. So you can have WKB wise, you can have both solutions. You can solve them exactly and have this. So, and you see that the exponential type solutions are good when the scale factor is really small, and the other that are oscillatory solution are coming with when the scale factor is larger. So this brings you some comfort, brings you some assurance that you might be getting something nice regarding having the early universe with inflation. But we will come to that in a moment. So next slide, please. So let it be there. So remember, please, that it is important when you are doing this either for any type of partial differential equation, second order, you need boundary conditions. So you either have the Arthur-Hawking or you have the Vilenkin. So now I would like to ask Giovanni if he is kind enough and he has the patience and the kindness to go to slide 12. So it's before this. This is slide 15. So it's before slide 12. Precisely. That's the slide. So let me just remind me. So I could have done the slides better, but I was in a rush to go to Sweden, so I didn't paste everything. So let's just remind ourselves of the figure of the that is in the center. So the center figure there. So on the left side of the center figure, you have the Hartle-Hawking proposal, the no boundary. You see that to the left of the barrier, you only have one mode of the exponential. To the right of the barrier, you have two modes for the oscillatory. In the Vilenkin or the tunneling, you have to the left of the barrier, you have two exponential modes, increasing and decreasing, and to the right of the barrier, you only have one mode. So now you ask me, why is this so? It is so because they propose to be so. These are proposals. You make a guess. So Vilenkin is taking things like the universe nucleates like an alpha particle. Hartle and Hawking do not want that. They want just to compute things inside the barrier using those dominant contributions from the less than half field and more than half field for sphere that dominate the path integral. And from that, you take everything that you have on the right. So incoming and outgoing. Please contrast this with the difference in the Vilenkin. Vilenkin only have the outgoing. So you are entitled to do whatever you want. The point is always to get a solution that you extract physical consequences that either are in agreement or disagreement with reality. So this is the greatest challenge of both boundary conditions as well as quantum cosmology as a whole. So please remind yourselves, keep in your mind the center figure on this slide, and let's go back to slide 15. Thank you, Giovanni, for your patience. Let's go back to
Can
slide
I ask
15.
something?
In the 15, precise, that's it. Now, press again.
Yeah,
a question,
please.
Professor.
One more press, one more item, please.
Yes, Professor, there is a question.
Yes, please.
In what sense do we mean no boundary in time? I didn't understand.
In the sense that you see the no boundary time. Can you write it or let's see. You mean the time there, this Euclidean time, right? Is this your question? So this Euclidean time that you have.
Orestes, please, can you repeat the question?
Or write it.
Or write the question, please.
But I think I understood. So
okay. Here.
About Vilenkin versus Hawking. So I don't know if I understood the question, but let me see. So they are both proposals, and you cannot decide mathematically which is better. They are both mathematically correct. It is just a matter of option when you are going to select what is your physical system. So for example, here for the Hartle-Hawking, as you see, you have that the wave, so the solution of the Hartle-Hawking HH that I have here in this line here below is a sum of psi minus and psi plus, where psi plus and psi minus are just different oscillatory solutions that are on the right of the boundary. So you see that these are like in outgoing and incoming that are oscillating outside the barrier. So the Hartle-Hawking, what is saying is that inside the barrier, I only have one exponential, which is that line there that has exponential minus 1, 3, potentially of V of phi, only one. And in the Hartle, and then outside the barrier, you have a cosine. That cosine is a sum of those two oscillatory solutions. So this is the case. So this is a proposal. It is as good as the Vilenkin, but they are different. They bring different wave functions. Why it is a no boundary? Then I need to go back to slide number 11. So slide number 11. Yeah, that's it. So the idea is that the wave function of your universe is computed on the hypersurface sigma. So this hypersurface sigma is a boundary. I know that this sounds paradoxical. So it is the only boundary, if in a way, is the hypersurface where you compute things. But whatever you can contribute, whatever you can consider, say the first half slice, or the second a little bit more than the slice, the other that is slightly deformed, or something that is like a donut, or something that is like a mug, they all have the same sort of hypersurfaces on top, if I may say so. So you don't have a boundary where to start. So you only have this hypersurface where you compute things. You don't care about what you have as the contributing, because this is the proposal by Hartle and Hawking. You only consider the saddle points that are compact. So all these images, all these figures that are here, they are topological equivalent. It is like a half sphere, more than half field or less than half field, but they are topologically the same. Consider like a football, and you slice like an orange. You can squeeze it in, you can enlarge it, but it's always half of a sphere, half of an orange. So all of them are similar. So the proposal of Hartle and Hawking is that you only take things that are compact, no holes. But then you say, what about having holes? What about having donuts and all those diagrams that you see in strings? Well, according to Hartle and Hawking, they do not dominate. So the solutions that are only important are the ones that are compact. Being compact means the first or the second image, there is only one hypersurface, and you don't care about the rest. There is no boundary. So it is a bit like Einstein many years ago, philosophically, he put this as the wholeness of the universe. You are only interested in the bulk of the universe. You don't get up anything about the surfaces. So it is a bit, I would say, topological as well as economical, in the sense that it takes away many confusion, but is a bit theological too. It is only something dominates and all the rest is superfluous. I don't know if I was clear about this?
Yes, thank you very much.
No worries. I will put in the references that you can look at it. So now, if Giovanni can go back to slide 15 again, where we were a moment ago, the next item, precise. So now you can see how we can do things in the Hartle-Hawking. You have this sum, psi minus plus psi plus. This is the cosine that are just above. You are adding this oscillatory with plus or minus I. So these are the oscillatory incoming and outgoing, and you get this cosine. Now, next slide, please. So in Vilenkin, it's different. Vilenkin knows that you can have ingoing and outgoing modes, but you only want oscillatory in this form. So next item, please. So Vilenkin oscillatory WQB mode is not a cosine, is a purely imaginary, it is a wave function that is oscillatory in the sense that is an exponential of the classical action. And you can get a notion of ingoing and outgoing where you define a current, things that go inside, outside of the surface. So it defines a current, please. Next item. He defines a current, he solves the equation, and for him, the Vilenkin wave function, the thing that is outgoing, he only wants the outgoing outside the potential is this. So please see the differences. Hartle-Hawking is a real wave function, a cosine oscillating, and for Vilenkin is this wave oscillatory in the sense that you have an exponential of an imaginary quantity. So please, next item, just to reinforce this aspect. Precisely. So the wave function is complex in the oscillatory or the classical region, whereas the Hartle-Hawking is real. So you may say, so are they different? Yes, they are. Which is mathematical correct? Both are. So how can we distinguish among them? That's the $2 million question. So this is where quantum cosmology, like many other more theoretical or mathematical aspects, are still open questions, but this is the thing that has dominated quantum cosmology since the 1980s. So it is with us almost for 50 years. Which is the correct boundary condition? Is there a boundary condition? How do we do things? So this is an open $1 million question to find something that is an imprint that will decide between one or the other. Can we do this? Well, next slide, please. Hence the question that may allow to distinguish. How generic is inflation? So let us believe, so you should see that there is a lot of faith here, leap of faith. So either Hartle-Hawking, no boundary, or Vilenkin tunneling. So you have to believe in it. So you need to defend it. You may do calculations in both, but they are both proposals. So the no boundary and the tunneling, they need to predict that there is an early phase of your universe that accelerates, what we call inflationary stage. They do that. So both predict that there are an inflationary stage. So good for them. So this is good. We have two proposals that allow at least to be according to the early universe that we want it to be. They both predict something, and I will come to that in the next slide, not yet, which is something that we call a strong peak. So the solutions are like an exponential, like a sort of a de Sitter solution, and the scalar field is sort of a constant, giving like a cosmological constant effectively. And you can, in these cases, you can associate to each solution of your WKB approximation a conserved current that is positively defined. How do you do that? You define J, like in a current in electromagnetism, you remember about that, and your J, which is your current, is the square of the amplitude with the gradient that is on the different values, the different expressions for your classical action. So you can have this, and you consider that you can define upon that probability density. So all this is very not wishful thinking, but this is very faith. It involves a lot of faith. Let's see how it works. So you define a probability density, D of P, which is just the value of the current that emerges from those hypersurfaces on mini superspace. So next item, please.
Professor, sorry, a question. Is this inflationary behavior, predicted by the two approach, Hartley,
Yes.
Hawking, and Vilenkin?
Yes.
Okay.
But there are differences, and you will see in a moment.
Okay.
So now the point, and this is the answer to your question, is the following. So you can prove, and these are works from Jonathan Halliwell in the late 80s, early 90s, I guess. where he proved that the probability density written as above, it's always positive definite. So you can say that this wishful thinking probability density is more than wishful thinking, is good probability density because it's positive definite. You can sort of normalize, you can integrate, you may opt to do things, but, and this is the difference regarding the question by Giovanni, they are different. For the Hartle-Hawking, and now you look at this, your probability density is an exponential of a positive function where the potential is on the denominator. Let's assume that your potential is a plane squared potential, like the chaotic potential for inflation. For Vilenkin, it is quite the opposite. It is different. There is a minus there. So it is -2 on the numerator, although the denominator is the same. So are these important? Oh, yes, they are. If you look at the first, if you now use your computer or your laptop or your cell phone or something, please plot either of these expressions where v of phi is just phi square. You will see that the first one is something that approaches asymptotically 1 at large values of phi, because it goes, so the exponential, the interior goes, so this goes exponentially of 0, so this means 1, and it goes to infinity for small values of the scalar field. Differently, when you look at what happens in the Vilenkin, it is basically 0 for small values of the scalar field, and the asymptotically approach 1 from less than 1. So in a way, the Vilenkin proposal brings you to something that is between 0 and 1. Just plot the expressions, whereas the Hartle-Hawking is something that goes from between plus infinity and 1. So in a way, they need a lot of careful when you are trying to do this regarding to have probabilities and consequences for inflation or not between both of them. I repeat, both are mathematical correct, both come from the Wheeler-DeWitt equation, and both are different because you decide, I want this boundary condition, I want this to happen at the barrier, and the other, you want another thing to happen at the barrier. You made a choice. Only when you made a prediction, and only when you go out and make more calculations to see if they match what you observe, in terms of experience, you may say which is the one that corresponds to the wave function of the universe. This is an open question, to my knowledge, until today. So next item, please, if you can press. So the no boundary has a probability that is for large values equal to 1, but this means that the value of the scalar field, and all the parameters are beyond the Planck scale. So this is really a problem. So next item, please, in this slide. So in the end, this is something. This depends on the potential you take, if it is squared, if it has a symmetry breaking, if it is an exponential potential or a power law. In both Hartle-Hawking and the Vilenkin allow you to have asymptotically the probability close to 1. I would say that the Vilenkin has one advantage, is that whatever you do to your probability density is always between 0 and 1. So you can easily normalize this. So it is always between 0 and 1. Whatever you do that, you square it and you integrate it through all the range. You can always bring something that you normalize in a way, almost. Hartle-Hawking needs more care. So this is just to say that we are in face of the first difference between the both solutions. Okay? Next slide. So we are getting more and more delicate. So we spoke a moment ago about peak, strongly peak. So I have no other way but to go to the evolution of quantum cosmology and to talk about Wigner functions. What is a Wigner function? So a Wigner function is something that you do with your wave function, and you construct a function where your domain is not the configuration variables of your mini superspace, but the phase space. You have, say, the scale factor, the scalar field, but you also have the momentum. So you sort of double your domain for another function, which is not the wave function we use in quantum mechanics, but something that is also wave-like and is called the Wigner function. This is very much used in quantum mechanics and when you want to extract behavior of complicated system. I will tell you in a moment. So the idea is that when your Wigner function has a sharp peak, please note that the difficulty in assigning probability here in quantum cosmology is that you do not have a Schrodinger equation unless you do something with your matter by hand, okay? And I will tell you in a moment. And it is not normalizable, okay? So unless you are doing things in a specific and limited range. So the Wigner function gives you a criteria to see if you are getting good quantum mechanics. If you have a peak, a high and sharp peak, and this usually is over a classical trajectory. So the peak of the Wigner function is something that spreads all over this phase space and where the momentum and the classical variables are correlated. This means that there is a sharp peak. So you identify momentum as the derivative of the classical action. And in mini superspace, you have a vector field that is orthogonal to the S, which is given by this expression. So this is just mathematics. So, but the question that you may come to your mind is, wait, am I sure that there is a single sharp peak? Is this nice thing to wait? It is nice for nice models, but most models are complicated. So next item, please. The problem is where you have your solution as a sum of different WKB contributions. You have different saddle points. You have different points where there are different contributions for your path integral. And you cannot bring one that is, say, of an amazing higher order, say 1 billion factor ordering, or say one larger than the other. So you cannot do this. So in the end, so what you have here is the possibility that different WKB solutions may interfere and you have quantum correlation. So this is where quantum cosmology is bordering quantum information and decoherence and almost those problems that you read about in quantum computation. But this is just mathematics, okay? I'm not making any claim. So the point is that when you have a peak, you have a correlation between momentum and variables. And you have this when your wave function is oscillatory. You can have this correlation when it is purely quantum, like an exponential of the Euclidean action, you don't have any peak. So this is good because you know in your solutions, when you study your wave function, your domains where it is inside, below, before the barrier or outside the barrier, you can find your Wigner function with these properties. There are good papers by Raymond Laflamme that has recently passed away and others, and they have analyzed this. So I have mentioned them also in the book. So next item, please. So how can we get out of this thing? Well, this is where different people have bringing different contributions. And this is the idea that has been along, say, either in quantum mechanics and now in quantum cosmology, which is also an open case, so there are still work to do. This has been, the pioneer in this has been Klaus Kiefer. So it takes that you will have an environment. So this is very strange, and I will have to ask you to postpone your questions, if you wish, until we go to another slide. So I'm trying to, in advance, to guess that you ask, what is this environment? Fair question. So let's take that you have the scale factor, the scalar field, and then you have fluctuations. Your noise. So noise, fluctuations, perturbations, something that is really below scale are your environment. When you take in your quantum system the environment, and you have off-diagonal terms, the off-diagonal, so this means the cross terms between the different WKV, and they are small enough. Again, this is a criteria. They might not be small, but if they are small, you can take that the quantum interference is much smaller than 1. So you see here all these quantum information things, quantum entropy and all of that, the matrix. So I will show you in a moment. So all this counts. So decoherence means that you have a process that you want it to work, where all the interference between off-diagonal terms are just damped, and the different WK branches just diagonalize, they separate, and you create, because there are no more correlations, you have classical behavior. However, this is assuming that the environment works and the back reaction on the environment is almost nullified. So you can have a semi-classical evolution. However, this only works in some cases. Okay, we are in a classical universe. This might be the case that brought us here. But I don't know, this has to do with this density matrix. I guess you have learned about it in your course. And this is something that we need to focus. So now I will ask Giovanni to go to not go. We will come back to here, but please proceed. Proceed. Next slide. Go ahead. Don't worry. We will come back to it. Next slide. Don't worry. No. Wait. Wow. This is too much. Before, yeah, precisely. That's it.
Okay. So
not this. It's the next slide. The one that says inhomogeneous perturbation. And then there is an item there with the bunch Davis. Please go. Just press. That's it. Let it be there. Let it be.
Okay.
So this is where we live somehow, still navigating by the coast, but where we are beyond mini superspace. So dealing with what we said a moment ago, and then we go back. We will still go back to the previous slide, don't worry. But if you look at those previous expressions, the lapse function now is n naught, depending only on time, and then you have a delta n that depends on space and time, so inhomogeneous. Likewise for the shift vector, likewise for the metric. So you could have only this omega ij, which is just Friedman, but you have epsilon ij. So these are hyperspherical harmonics. Likewise for the scalar field. So you are taking inhomogeneous perturbations. You are doing like a Fourier sort of expansion in small fluctuations on your mini superspace variables. Can you do this? You must do this. So what happened is that then your action, the one that comes from your Einstein-Hilbert, your action is the sum of two terms. S naught, which is just your mini superspace action, and S2. S2 always depends on whatever you had before for your mini superspace, but now you have all the perturbation, all the fluctuations are there. You have integrated this on the hypersurfaces. You have to do a lot of integrating on the free sphere. And in the end, what do you get? You get that your Hamiltonian constraint is a sum of two Hamiltonian constraints, one that is the mini superspace that we used before, and something H2. So the H naught is it's just the plain thing. H2 is what it's written down here. It's a sum that has like an harmonic oscillator, which is a mass term or a potential term that is almost like time. It's not real time, but it's depending on the scale factor there. So it is something that, how do you solve this? Well, you write your wave function as your WKB thing just for mini superspace with a psi with this hat. This psi with a hat satisfies a Schrodinger equation. You have to do the calculations, okay? You have to believe me, trust me. It takes pages and pages to go here. So this H2, which is the Hamiltonian constraint on the perturbation, satisfies a Schrodinger equation on a time that is extracted from the WKB time. We will go to there, just allow me. And your psi hat is a product of several psi tilde that depend on time and also on the perturbation of the scalar field. So this was a work done in 1985 by Jonathan Halliwell and Stephen Hawking, where they calculated this, and for the first time, then others did this for other. For the first time, they could compute a physical consequence of the no boundary of the Hartle-Hawking solution, in the sense that you could have perturbations in matter that were fitting with Kobe data. Now you can do this reasonably well with Planck, and also I will point to that. So the point here is that now, this century, either the no boundary or the tunneling, you can get a Schrodinger's equation like that, and a particular vacuum state, which is the Bunch-Davies vacuum. So this is something that is like a de Sitter thing. Now I need to ask you, Giovanni, to go back to the previous slide. Precisely, yes, that is okay. So maybe when I wrote this slide, I should have permutated these two slides, but they came like this, so okay, don't worry. Now we are okay. So the point here now in quantum cosmology, and you can see how things get really confused and messy and heavy and dense, is that you have now two sort of degrees of freedom. You have global between quotation marks, degrees of freedom, say the scale factor from a Friedman model, the scalar field, whatever you want. And then you have fluctuations. These can be the perturbation terms on the scalar field or even gravitational waves, say gravitons. So these are the environment. These are your noise. So you have something that evolves, a Friedman model with a scale factor, a scalar field, and you have something underneath that is fluctuating, the perturbations, the environment. So now you have a density matrix, and you want to have a reduced density matrix. So you are going to sum over all the perturbation, over all the environment. So you have here your density matrix. This is something that is really well explained and exposed with a lot of detail in Klaus Kiefer book and in the papers, I think, by him and also Raymond Laflamme and others. So the density matrix, the reduced density matrix, here is the trace where you are summing over the perturbations of the scalar field. So this means that rho on the gravitational degrees of freedom becomes a rho of A1 and A2, so just two scale factors, which is just this function psi naught A1, psi naught complex conjugate A2, and this very complicated product, which is called the decoherence functional, and where each of these tilde psi n satisfy this sort of Schrodinger equation, where t is the WKB time. Please note that d by dt is this mathematical symbol. It's not an equality like 2 equals 2 or 2 plus 2 equals 4. You assign that the gradient of S along directions orthogonal to hypersurfaces on A with the gradient on A, this is what you define, this is what you call, you designate as a time, because you are going from hypersurface to another hypersurface. So hence the 3 parallel lines there, you define as such. It is your WKB time. Why? Because if you do this, you can write that. You can write a very nice Schrodinger equation and you can solve it. And you ask, well, why should I do that? Well, because you obtain very nice solutions which can be Gaussian, and you get away with all those quantum coherence that destroy your classical time, and then your classical description, I'm sorry, and more than that, you get a vacuum, which is like the de Sitter vacuum of inflation, which everybody now calls the Bunch-Davies. So you get things that are according to what you observe in quantum field Turing curve spaces for our universe. So the WKB time allows you to do that. Of course, there is a price to pay, is that you need to go up to a level where the WKB components do not interfere. So you are but when you have a turning point in your WKB, this is bad. You may not have this WKB time, and more than that, you may have back reaction and destroy all these things. So this also is very well described in the book by Klaus Kiefer. Let me just say to you one thing here, is that everything that we mention here, this is something that goes from the mid-80s to the late 90s or even early 20th century. So this is nearly 3 decades of work. And I have put this very dense, very compact in these slides. So most details are not even here. For that, you will need to write an enormous book. Maybe now with artificial intelligence, they can do this. So is everything okay until here?
Yes.
Okay. So
okay. Thank you.
okay. So let me just. So I have only 4 more slides. I don't know if I have time. You must tell me if I have time. So it is almost it's 20 past 5 here in Portugal. How about you and the students?
Yes, we are okay, Professor. You have more time you want.
Okay, so let me just, I will come back to that. So like I make a bridge between my lectures, and let's go now to a bit towards the future. Not yet the future, but also something that I need you to believe. You can do the calculations like many people have done, but now we are moving to another structure in quantum cosmology. So please, next slide. Now the other one, this we have already seen. It's press, then next slide. Okay, so there it is. So far, so I'm going now the next slides, and tomorrow I will talk about what can be done besides whatever I already talked about as open problems, things that are still yet to be chased and resolved. And you are the young people, and you should, if you like quantum cosmology, this is where you may consider to do some research to find solutions or solve problems or correct things. So you can consider quantum cosmology with supersymmetry. So this is an immense open discussion. I will only present here, and I will send to Giovanni, as I said, the PDFs of those references. So how do you do this? So the point here is the more elegant thing to do is a bit like following on the footsteps of others, in particular, what like Claudio Teitelbaum or Brewster, I know he's changed his name, have done, which is picking up n equals 1 supergravity. Don't ask me what is n equals 1. You can ask me, but this means only one gravitino. So this means that besides you having a graviton, you have supersymmetric partners. So you need to know a little bit of supersymmetry. But bear with me, you will see how this is so rich, even if you don't use supersymmetry so explicitly. So consider supergravity, which is the supersymmetric generalization of general relativity with one gravitino. So this means that you take your action, which is not the Einstein-Hilbert, but is supergravity. Then you make a simplified assumption, maybe too simple. This may raise enough problems already. Take Friedman models. So this is really a bottom-up prudent approach. So you start simple. Let's see how it goes. It will be complicated and troublesome enough. So next item, please. So this will bring you a reduced action from n equals 1 supergravity. You put a Friedman model with some choices, you integrate on the free volume, and you get a new quantum mechanical system that has invariance under time translations, like quantum cosmology had, plus supersymmetry, plus Lorentz invariance. So you get a lot of things. Some are good, some become things much more complicated. Why do I mean that it becomes complicated? Next item, please. Because, as you see, you need now to use spinors and you need to use a tetrad. So you use a tetrad in a two-spinor notation. So please, I know I'm being very detailed. You haven't perhaps learned about this like I haven't many years ago, say 30 or 40 years ago in my life. I had to learn this, but I learned it. So this is something that Penrose and Rindler developed. So you have a tetrad, which is a sort of a square root of your metric. If you consider a tetrad like this matrix here, and you square, you multiply this diagonal matrix by itself, you get n square, a square. So this is what you have. This is what you have in your metric, your plain Friedman metric. The scale, there is a lapse function, which is n square in your metric. We are not going behind a lot of slides, but you can see this in the earlier slides of this talk. And then you have a square. So this is just the inverse thing. The important aspect is that you have here a capital A and capital A prime. They vary between 0 and 1. This is just a notation, a bivial. Please bear with me. I know this is more and more detail. If this is just your first contact, and you are using this because when you take spinors, like the solution of the Dirac equation, you can only work with spinors on a tangent space. So you need at each point of your manifold to have a tangent space where you can work with spinors. So the tetrad allows you for the mu index, which is an index of your four-dimensional manifold in your space-time with curvature, with strange topology, and you have the lowercase a, which is what links you to the tangent space. This thing with this sigma here, which is more or less almost like the Pauli matrices, allows you to use these two spinor notation. So this is very dense. Please bear with me, and you will see how this is useful. Next item, please. Then you make the ansatz for your gravitino. You have to do it. If you choose your gravitinos, which have spinorial indices, and space index is like this. Okay, so and you get next item, please. In the end of the day, I'm not putting things here all together. You get a mini superspace, which is Friedman with n equals 4 local supersymmetry. Please, before we continue, let me just say the following. You start with n equals 1 supergravity in 4th dimensionals. That's what it's on the first line. You have a 4-dimensional n equals 1 supergravity. So n equals 1, 4-dimension in space-time. Then you put a Friedman, you make some choices, always choices. You integrate on the hypersurfaces, and you get a quantum mechanical mini superspace with only time dependence, but with n equals 4. It's like the 4-dimension in space-time permeates to n equals 4 supersymmetry. So this is a sort of problem, because you can construct things artificially with n equals 2 supersymmetry, but it seems that when you do things supergravity-wise, it's n equals super 4. Now let me ask you, this is almost 5:30. Shall I stop here for tomorrow, for not to be too heavy? And then tomorrow I will continue talking about this and fractional quantum cosmology, chaos, additional things, observational quantum, everything that is new for the 21st century, which I will not see because I'm 63 years old and my event horizon is approaching, but you are young and you might work on it. Giovanni, what do you advise me?
It's okay. Thank you, Professor. I think yes. We are going to continue tomorrow, no, with the last season, and then it's okay for today, no.
Yeah,
Also,
a lot of things.
yes, there are questions.
I'll send you the books in a moment.
Okay. Any questions?
Hello, Professor.
Yeah.
Can you hear
I'm
me?
here.
Mm.
Yes, I can hear you.
Okay, I still don't understand in the Hawking-Hartle case, how do we have both an outgoing and ingoing wave? Because when we have a standing wave, we have also a boundary. It has to reflect to come back.
Yes. The
What
question is not
what is the
how do we
boundary?
have. It is not a question of having, it's a question of choosing. You want it to be like that. It's a proposal. The proposal of Arthur Hawking is that you have the barrier, and here you only have one exponential. So here is Euclidean, you have only one exponential. And here you have outgoing and ingoing. You have both oscillating. You decide to do that.
Yeah, but to have something coming back, it has to reflect somewhere, not.
No, it is a consider. Let's do like this. Consider plain Schrodinger equation with a barrier, the tunneling barrier with the rectangular barrier. If you go and solve the Schrodinger equation outside the barrier and inside the barrier, you always get here the incident and the reflected, and here you also have the both of them. If you solve Schrodinger equation outside the barrier, you always have two modes. You decide when you are studying your system that you have an incident wave, goes to the barrier and reflects, and then it goes through and then it tunnelates. This is your choice. You decide when you are solving your Schrodinger equation that the amplitude of the incoming is 0. You go to a quantum mechanics book and you see that let's put this 0 because it's only the transmitted wave that interests to us.
Yeah, but this suggests that it was ingoing at first, it passed through the potential, and then you have also the reflected and the transmitted. Here we don't have this. It's not the same, right?
The Vilenkin thing is more like
The ranking is
alpha
like alpha
particle.
particle. I
It
understand
makes
that.
sense.
It makes sense,
The
of course.
Vilenkin the Vilenkin proposal is more realistic. Is minimal, is more realistic. You only have something coming out. But the Hartle-Hawking is something that, okay, I want both because I want a cosine. You do it. But then they say, well, wait, let's do calculation and see if we can obtain for our proposal good physical predictions. And they do.
Okay, I will think about it. I will ask you tomorrow again.
Okay, no problem. You go to a quantum mechanics book and you see that for the rectangular barrier, you have the incident wave, the reflected wave, and then the author of the book says, well, the wave that is transferred, the one that it's only the outgoing. So we put d equals to 0, so you don't have the ingoing. But this is your choice because you consider the ingoing non-physical. Not for Hartle-Hawking, they say it's physical.
Okay, thank you very much.
Okay,
No
thank
problem,
you.
my pleasure.
Yeah, good. Thank you, Orestes. Any other question? Yes, I think
Tomorrow, same time.
I think this question is basic. I think yes, but perhaps it's important. Yes, in both approach, even in Hartley-Hawking and also Vilenkin, we are obtaining something like a Schrödinger equation, understanding, no? And then, but this is a non-relativistic equation, and then, but gravity is relativistic, and then why we are obtaining a Schrödinger-like equation, you know, I don't know, a relativistic equation.
It is, you are taking, it is a worthy question, but the point is that you get the Schrödinger equation for the propagating matter modes on the mini superspace. So this means that it's almost like semi-classical cosmology or quantum field theory in curved spaces. That's what you get. So I understand your point, but that's what you get. You get a Schrödinger equation with some quantum gravitational corrections. And this is something that is possible.
Okay.
It's not entirely relativistic. For that, you have either the Dirac or the Klein-Gordon, but this is something that you get as a consequence of using these correction terms. Again, as I said, you are seeing here a couple of, say, almost like 40 slides, including tomorrow. I put in 40 slides more than 40 years of quantum cosmology. So those 40 years should be like 4 volumes of a book. So there is a lot of work, and quantum cosmology has not yet been vindicated as something that you identify in the sky a proof. There are no proof that the universe got a quantum mechanical origin. You don't have it yet. It is consistent, but you don't have a smoking sign of the gravity. I mean, matter, quantum mechanical matter, yes, but it's quantum gravity.
Okay.
Tomorrow we'll talk more about it. I will send you in a moment for your email the files, and you can share with the students.
Okay. Thank you. Thank you, Professor. Thank you, Professor.
No problem. I will do it in a moment.
Okay.
See you tomorrow then.
See you tomorrow. Yes.
At the same time.
Bye
Okay.
bye.
See you tomorrow.
Yes. Thank you.
Bye-bye. See you.
Thank you.
Bye.
Thank you. Thank you. Bye-bye.
Yeah, thank you.
Bye bye.